Okay, so I'll begin now. So this week we'll be learning about rotational motion. So first, we'll talk about describing rotational motion. So when we work with rotational motion, we describe the motion as it moves in a circle, and we use angle theta to do so. And also angles are measured in radians. So as you see in this diagram, this angle is the change in theta, the change in angle, and this right here is the arc length, and this one here is the radius. So to find angle theta, when we delta theta, which is the change in theta, is equal to the change in the arc length divided by r, which is the radius. So, and if a particle travels around the entire circle, the distance is 2 pi, because the entire circle's distance is just the circumference, which is 2 pi r. So it would be 2 pi r divided by r. So it would be 2 pi. And also, some units over here are 1 rev is equal to 360 degrees, or 2 pi rad, and 1 radian is equal to 1 radian times 360 over 2 pi, which is, so 1 radian is equal to 57.3 degrees. Okay, so now this is another conversion. So this is the angle in radians, and to find the degrees, to get rad, you get the degree times pi over 180, and to find degree, you just have the rad times 180 over pi. So next we'll just do example for rotational motion. So I'll give you 2 minutes to do this. Okay, so it says, while riding on a carousel that is rotating clockwise, a child travels through an arc length of 11.5 meters. If the child's angular displacement is 165 degrees, what is the radius of the carousel? So the equation you would use is theta is equal to the arc length divided by r. And you try to find r here, so it would be r is equal to the arc length divided by theta. So it says angular displacement is 165 degrees, but it should be in radians instead of degrees. So based on this the top one, this is the radians is equal to the degree times pi over 180. So it would be rad equal to 165 degrees times pi over 180, and you would get 2.88 rad. So you can just plug it in now. So it would be R is equal to 11.5 meters divided by 2.88 rad. And you would get 3.99 meters. Okay, so now I'll talk about angular velocity. So angular velocity is how fast something rotates around an axis. Angular velocity is equal to the angular displacement divided by the time interval. So in this picture, you see that this is the time from one position to another. So this is the change in time, and this is also another thing is it says W is equal to theta over T, but it's not actually W, it's omega. So it would be omega is equal to the change in angular displacement divided by the change in time. So this change divided by the change in time. And the angular velocity is constant for a particle moving with uniform circular motion. And the unit, instead of for velocity, which is meters per second, the unit for this one would be rads per second. So it would be R over S. Okay, so now I'll talk about how speed and angular speed relate. So since we know that omega is equal to theta divided by time, and we also know that speed in linear motion is equal to the distance divided by time. So in here, you see that, and also here. So it's over t. So in a circle, for linear motion, instead of d, it would be s because it would be the arc length. And we know that b equals s then, which equals r times theta, since theta is equal to s over r. So that now since we know that the arc length is equal to r times theta, we can plug it back into this equation. So it would be r times theta divided by, so it would be r times theta divided by t. And using this equation, which is omega equals theta over t, we know that theta over t is equal to omega. So you can just use this part and do v is equal to r times the angular speed. And this is also called the tangential speed. And now I'll talk about angular acceleration. So if you push on a bicycle wheel, it will rotate, and as you continue to push it, it rotates faster. And since the angular velocity is changing, there's an angular acceleration. So angular acceleration isn't just A, it's alpha. So alpha equals the change in the angular velocity divided by the change in time. So it's angular acceleration is the rate of change of angular velocity. If the object rotating is rigid, all points on the object will have the same angular speed and acceleration. And rigid bodies are shapes that don't change, and their shapes will always be the same, and they won't be deformed. And also for angular acceleration, instead of acceleration, which has the units of meters per second squared, oh, this is wrong. The unit of angular acceleration would be rads per second squared. Okay, so I'll talk about tangential acceleration now. So in this diagram, since last week we learned that the centripetal acceleration always goes to the center. So this right here is the centripetal acceleration. And we learned that the centripetal acceleration is due to the change in the direction of the particle's velocity. The centripetal acceleration is also directed toward the center, as I showed. So since the angular speed is changing, there will be another component to its acceleration, which will be tending to the circle, which is this right here. So this is known as a tangential acceleration. The tangential acceleration is equal to the change in the speed over time. And since we know that the velocity is also equal to the angular velocity times r, you can write this equation as delta omega over r equals delta t. But we can just put as delta omega since the r is going to be the same, t times r. And we know this in our previous equation is just the angular acceleration. So we have the tangential acceleration is equal to alpha times r. It's also shown here. Okay, so now you guys can do this example for angular acceleration. Okay, so for this question here, it says a car's tire rotates at an initial angular speed of 21.5 rods per second. The driver accelerates, and after 3.5 seconds, the tire's angular speed is 28 rods per second. What is the average angular acceleration during the 3.5 second time interval? So the equation for angular acceleration is the change in angular speed divided by change in time. So the final minus the initial angular speed divided by the final time minus the initial time. So we know the change in time is just 3.5 seconds, and the final angular speed is 28, and the initial is 21.5. So we can start 28 minus 21.5 divided by 3.5, and you get 6.5 divided by 3.5, which is just answer be 1.86 rods per second square. Okay, so now I'll talk about linear motion and rotational motion. So for position in linear motion, we would just use x, and rotational motion we use theta to represent the angular position. In linear motion, we use v for velocity and a for acceleration. In rotational motion, we use omega for angular velocity and alpha for angular acceleration. So the big five equations we use for kinematics and linear motion are these, and they're the same thing in rotational motion, just with different, it just looks different. So instead of x, it's theta is equal to angular velocity times time, and the final angular velocity is equal to the initial angular velocity plus angular acceleration times time. And then angular position is equal to the initial angular velocity times time plus 1/2 angular acceleration times t squared. And the final angular velocity squared is equal to the initial angular velocity squared plus 2 times angular acceleration times the angular position. So now I'll talk about torque. So torque is the torque is the rotational equivalent of force. However, torque is different from force because when you want to make an object move, you apply force on it. But when you turn or rotate an object, you exert torque instead. So torque is just the rotational equivalent of force. So torque depends on the magnitude F of the force, the distance r from the pivot. So in this diagram right here, you see that this is the pivot and this is the r. So this is the r we're talking, the distance we're talking about, and the magnitude F of the force, which is this one, and the angle at which the force is applied. So it's this angle. And the force always has to be perpendicular to the distance. So if you see this diagram right here, instead of this F times this R, it has to be this one. So this one's the one that's perpendicular, which is why the equation for torque right here is torque equals the force times the distance times sine theta, because you're using this component instead of this one. And also this isn't just t, it's tau, which is degree for t. So it'd be tau is equal to torque is equal to force times distance times sine theta, with F being the force and R being the distance from the pivot. So to have balance torque right here, this isn't a balance torque right here was equilibrium, and this is a non-equilibrium torque. So equilibrium torques, you see right here, it would be the torque for this one is equal to the force times the distance, and it would be sine 90 because it's already perpendicular. So it would the angle would just be equal to 1. And then right here, the same thing, it's the torque for 2 is equal to the second force times the second distance. And again, it's sine 90, so it's V1. So this is equilibrium because the torques are equal and they're opposite. So it's torque 1 is equal to negative torque 2. So the net force without would be equal to 0. So since the net force is equal to 0, there's no net external torque. So the object at rest stays at rest. And then for this one right here, this part is equal to torque 1 is equal to force 1 times the length 1. And this one's also equal to torque 2 is equal to the force 2 times length 2. But you can see that the distances are different. So torque 2 is definitely going to be bigger than torque 1. So instead of the sum equaling 0, there will be a net torque. So since there's a net external torque, the object experiences angular acceleration. Okay, so now here's example 3. And I'll give you 3 minutes to do this, 2 minutes to do this one. Okay, so it says a 150 kg man stands 2 meters from the end of a diving board. So if we draw it, it would be, since the water, this is the point, and this is 2 meters. And this is a person whose mass is equal to 150 kg. So how much torque does he apply at the base where the board is attached, assuming the board remains horizontal? So it's actually for the torque, which is F times R times sine theta. And since he's perpendicular, it would just be sine 90, so it would be 1. So it's just 2 times, wait, oh, it would just be 2 times, since the force is just mg at this point, which is the gravitational force, it would be 150 times 9.8, which is 150 times 9.8 and then times 2 meters. So now I'll talk about moment of inertia. So since torque causes angular acceleration, we can write angular tangential is equal to the force divided by the mass. And we know that this is equal to the angular acceleration times r equals force over m. And if we divide that, it'd be angular acceleration is equal to force over mr. And we also know that torque is equal to r, which is the distance times f. So it says F is equal to torque divided by R. So then we can start over here, torque over R is equal to M times R, which is just torque times mr squared. And Newton's second law is F equals ma, which is written as F over m. And we know that F is the torque is the rotational equivalent to F, and angular acceleration is the rotational equivalent to A. So mr squared must be the mass. So moment of inertia, which is I, equal to mr squared. And also moment of inertia and mass are different things. So this is Newton's second law of rotation. So an object that experiences a torque about the axis of rotation undergoes an angular acceleration for I, the moment of inertia of the object. I is the moment of inertia of the object by the rotation axis. So in here, we know the angular acceleration is directly proportional to the net torque, and the angular acceleration is inversely proportional to the moment of inertia. It would be like torque over I. This is the net, this is the net torque. And there's a difference between moment inertia and mass. The moment of inertia depends on the quantity of matter and its distribution in the rigid object. And the moment inertia also depends upon the location of the axis of rotation. So just remember this formula because it's important when solving questions. So these are also some common shapes for moment of inertia. So for a solid cylinder or disk here, the moment of inertia would be 1/2 mr squared. And for a hoop, it would just be mr squared. For a sphere, it would be 2/5 mr squared. For a rod about its center, it would be 1/12 ml squared, which is just the length. Then for a solid cylinder, for its center diameter, and this is for the symmetry axis, it would be 1/4 ml squared plus 1/12 ml squared. And for the hoop about its diameter, it would be 1/2 ml squared. And for a thin spherical shell, it would be 1/2 ml squared. And for the rod, it would be 1/3 ml squared. And you don't need to memorize these right now. So you can start doing questions. So I'll give you a few minutes to do question 1. Okay, so I'll start. So it says if it takes a bike wheel 3 seconds to complete one revolution, what is the wheel's angular velocity? So the equation for angular velocity is the change in angular displacement and time. So one revolution is 2 pi, so it'll be 2 pi, and the time is just 3, which equals 3.09. So it'll be this one. Okay, so this is the solution. And now here's question 2. So it asks, what is the angular velocity of the second hand or clock? So this equation, angular velocity is equal to theta over t. And you know t is equal to 60 seconds because that's how much time it takes for the second hand to complete one revolution. So it would be to complete one, it would just be a full circle, which is its circumference. So this is 2 pi over 60. So that would be equal to pi over 30, which is 0.14. So this is the solution here. Okay, so this is question 3. Okay, so this question asks, what is the difference in the angular velocity of the second hand of radius 1 centimeter on a wristwatch compared to the second hand of radius 5 meters on a large clock tower? And the answer is both. Uh, I forgot what the answer is in here, but the answer is no difference. So here's just leave that. Um, since the angular velocity should not change based on the radius of the second hand, no matter what size the second hand, it will still cover one revolution every minute or 60 seconds. So in this equation, it's always going to be the same. This is question 4. Okay, so for this question, it says a Ferris wheel has a trip length of 3 minutes. It takes 3 minutes for it to make one complete revolution. What is the angular velocity of the Ferris wheel if it only takes passengers around one time in rounds per second? So the equation is the angular velocity is equal to theta over t. So to one revolution is just 2 pi divided by 3 minutes versus 20 seconds, it's 180 seconds. Versus pi over um, it's equal to 0.035 radians per second. So here's the answer. And this is question 5. Okay, so it says a wheel makes one full revolution every 2 seconds and has a radius of 5 meters. Determines angular velocity. So the formula for angular velocity again is over time. So if it makes one full revolution, 2 pi over 2 seconds, so it says pi or per second. So they just put that into 3 I guess. This is the solution. And this is question 6. Okay, so it says a wheel horizontally, a horizontal wheel, a horizontally mounted wheel of radius r is initially at rest and then begins to accelerate constantly until it has reached an angular velocity omega after 5 complete revolutions. What was the angular acceleration of the wheel? So we use one of the kinematic formulas. So it'd be inertia squared plus 2 the acceleration times theta. So they give you theta is 5 though, and we do it change that to rad. So it'd be 5 times 2 pi. So it'd be 10 pi. So since this is going to be 0, so it'd be equals 2 times acceleration times 10 pi. So I guess acceleration is going to be the velocity final squared divided by 20 pi. So here's the solution. Okay, so this is question 7, and this is a torque question. So don't forget that the equation for torque is force times distance times sine theta. Okay, so this question says a bolt connecting to the main and rear frame of a mountain bike requires a torque of 15 newtons per meter. To tighten, if you are capable of applying 40 newtons of force to a wrench in any given direction, what is the minimum length of the wrench that will result in the required torque? Using this formula, um, the sine, it, we can just make it sine 90 in its any direction. So it would be R is equal to T over F, it would be 15 newtons times meter over 40 newtons. So that would be 0.375 meters. So this is the solution again. Okay, so you guys can do question 8. Oh, actually, that can just do question 9 instead. Yes. So for this question, says there's a 100 kg weight 3 meters to the left, the center of the seesaw. What distance from the center on the right of the seesaw should Bob sit on to support the balance? So the torque is equal to 3 times 1,000. This is the force. So the force is equal to mv. So 1,000 times 10 would be, oh no, sorry, 100 times 10. Would be 3,000 newtons. So then the other side would be torque is equal to 3,000. Torque is equal to R times Bob's math is 60, so 60 times 10. And we're also assuming that sine is 90 degrees. So it would be 3,000 equals 600 R. So R is equal to 5 meters. So here is the solution. And this is the um, um, the final question. Okay, so for this question, it says two masses hang below massless meter stick. Mass 1 is located at the 10 centimeter mark with a weight of 15 kg, while mass 2 is located at the 60 centimeter mark with a weight of 30 kg. At what point between the two masses must the string be attached in order to balance the system? So, so this is the 15 kg, this is the 30 kg, it's the 60 centimeter mark, and this is the 10 centimeter. So, and this what the string should be. Let's say this is the x. So we need to balance these out. So this right side would be, so this distance would be just like x minus 10, which is the distance, times f, which is mg, would be 15 times 10, and that's equal to this side. So if since this is further, it's 60 minus x times mg, so it's 30 times 10. And since we can cancel the g, so it's just, and if we expand that, be 15x minus 150 equal to 1800 minus 30x. So if you move the x to that side and this to this side, we get 45x is equal to 1950, and x is around 43. So this is the 43 centimeter mark. This is the solution. Okay, so that's it for this week. I hope you guys have a great weekend, and I'll see you next week.